To understand why the Titanic was lost, we must map the exact timeline of the 1912 disaster. By tracking the ship's final hours, we can measure the mechanical and logistical failures that dictated the outcome. The ship's primary defense was a compartmentalized hull. This diagram shows the sequential watertight sections along the lower deck, designed to isolate damage and maintain buoyancy. On the night of April 14th, the vessel operated in an environment that masked its inherent danger. The North Atlantic was perfectly calm, hiding water temperatures that hovered at the freezing point. The sinking progressed as a measurable sequential failure of two distinct systems: structural buoyancy and evacuation logistics. Moving past the popular myths allows us to examine the specific physics and mathematics that governed the system's collapse. The iceberg acted as a rigid physical mass. Its density violently altered the state of the hull the second the two objects intersected. The collision tore the starboard metal plates, sending a physical vibration through the vessel as the structural system began to fail. This wireframe tracks the mechanical breach. The impact simultaneously breached the first 5 forward compartments, exceeding the system's tolerances. Because the bulkheads did not seal to the ceiling, the sinking bow caused seawater to spill into the adjacent dry compartments. This created an accelerating loop, spilling into the next compartment in a continuous chain. Plotting this failure over time, we see that from the moment of impact, the ship's structural integrity enters a steep, measurable decline. Once water moved past the final bulkhead, the total loss of structural buoyancy became a mathematical certainty. With the structure failing, survival relied on evacuation logistics. The scale of the passenger decks suggests an immense volume of people compared to lifeboat capacity. This chart shows the hard limit of the backup system: 2,200 people on board, against a maximum lifeboat capacity of just 1,178 seats. Integrating this into our timeline shows the survival system began far below the required baseline for the total population. The evacuation lacked a centralized ship-wide alarm. Without a coordinated signal, information reached different parts of the ship at different times. This communication gap led to extreme inefficiencies. On the upper decks, lifeboats sat unused, while the lower compartments were already taking on water. Officers managed the evacuation using a localized interpretation of the Women and Children First protocol, frequently preventing men from boarding, even when seats remained open. This bar chart visualizes the drop in utilization. Several early lifeboats launched at less than half of their engineered capacity. These errors bled away critical time and permanently reduced the available evacuation capacity as the ship continued to sink. The lack of physical boats established a low ceiling for survival, while loading inefficiencies further reduced the actual number of people saved. In the final phase of structural failure, the stern rose out of the water. This forced the remaining 1,500 people into the surrounding environment. The North Atlantic Ocean was 28 degrees Fahrenheit that night. This chart tracks biological thermal degradation. Human core temperature drops rapidly in freezing water. While cork life vests kept people afloat, they provided no insulation. This overlay shows the threshold for cardiac arrest, occurring long before a person would drown. Survival was determined by a single variable: whether a passenger secured a seat inside a dry lifeboat or entered the water. For those in the ocean, movement eventually ceased. Biological systems failed within minutes, followed by silence across the surface. The freezing ocean acted as an uncompromising timer, ending any possibility of survival for those not in a boat. The vessel lost all remaining buoyancy and disappeared, leaving only the scattered lifeboats on the surface. 2 hours later, the RMS Carpathia arrived. This functioning maritime system was the final variable in the disaster timeline. The rescue operation followed a strict logistical path. The Carpathia recovered the intact lifeboats, but could not assist those who had already succumbed to the thermal limit of the water. Of the 2,200 people on board, 705 survived to be recovered by the Carpathia. The final survivor count was the exact mathematical result of total lifeboat capacity minus the launch inefficiencies. The disaster data transmitted globally, creating an immediate demand for answers regarding the failure of such an advanced engineering system. The public and the engineering communities had to reconcile the vessel's technological status with the final catastrophic numbers. This tracker provides the central insight of the investigation. Advanced structural integrity cannot replace adequate evacuation logistics. Both systems must function together. Regulatory bodies immediately mandated that all passenger ships carry enough lifeboat seats for 100% of the people on board. New rules required 24-hour mandatory radio watches to prevent the communication gaps seen in the early hours of the sinking. The sinking serves as a foundational case study in failure analysis, modernizing maritime safety systems worldwide. The disaster remains a lesson for all engineers. Systems must be scaled for the absolute worst-case variables, or the